Okay, let's continue. So we are doing chapter 3, the final part to chapter 3. So last time, let's do a little recap first. New slide. Okay, so we talked about systems in equilibrium and also systems in linear motion. So at this point, you guys are like bored already of this system in linear motion, system in equilibrium and linear motion. Sebab kita dah go over a lot of examples and we have done like 4 parts of this. 4 classes. So system in equilibrium means that your net force acting on the object is equal to 0. What does that mean? It means that you have 0 acceleration. Therefore, you will have conditions where V is constant or V is 0. So this is your situation. And then when you write your when you draw your free body diagram, you start with your free body diagram. You start with your free body diagram and then you start with your your condition. Condition. Okay, and then you go for your equation from your free body diagram. So free body diagram penting This is the first step that you should do when you tackle a force punya problem. Free body diagram, and then you determine what is the condition. How do you know the condition? You look at the question. So for a system in equilibrium, the net force is equal to 0 or the acceleration is equal to 0. Typically, this is when the object is not moving or moving in a constant velocity. So you have to identify the keywords in your problem to identify whether it is in equilibrium or not. So when you have identified that it is in equilibrium, you know that you should start with net in the fx equals to 0, net in the fy is also equal to 0. And whatever that your free body diagram has, let's say you have a box on a table, the typical example that we have, this is your x-axis and this is your y-axis. And whatever forces that you have, F1 ke, F2 ke, F3 ke, F4 ke, whatever that is in your free body diagram on the x-axis, you write it in your equation. So let's see, this is positive F1 minus F2. It can be any forces. You don't have to be restricted to the ones that we learn. It can be like a random force, not random lah maksudnya, it's just a magnitude of force lah. So it can happen like this. So and then you have F4 positive going upwards, positive, positive, and then going downwards is F3. Need to pin myself. Add pin. Oh, why is Arman pinned? Remove pin. Okay. Okay, so this is how you tackle it lah. If there is an unknown, you can solve using the equal to 0. Okay, so that is system in equilibrium. And then we move on to system in linear motion. Okay, so this is the new part that we learned. Sorry to samburu hari ni. So this means that your acceleration is not equal to 0, which means that this guy should be moving. Moving macam mana? Moving upwards or moving to the left or right. Okay, it can also move downwards lah. Moving up or down, and then moving left or right. But here, the velocity should not be constant. Okay, velocity should not be constant. It's not constant. Okay, so it keeps on changing. Therefore, you have acceleration. Okay, so we have system in linear motion. Now, when it is moving up and down, you know that your net in the Fy will not be equal to 0, which means that it is going to be equal to MA. I think someone is not muted. Okay. Okay, so net in the Fy is equal to MA. However, if it's just moving up and down, okay, if it's just moving up and down, but it's not moving to the left and right, therefore, you only have net in the Fy equals to MA, but your net in the Fx is equal to 0. So you have to remember that the MA only applies to the axis yang the object is moving. So for example, I have a car This is an ugly car. Okay, so it's moving to the right and it is accelerating, but the car is not flying. Therefore, your net in the Fy is equal to 0 and your net in the Fx is equal to ma. What does the m refer to? It refers to the mass of the object. In this case, it's the car. What does the m refer here? To the person that is trying to fly. So it depends on what object that you're talking about. That is your m. Okay, what else? I told you if you get acceleration is equal to a negative magnitude, it simply means that your assumption of the acceleration punya direction is incorrect. Your assumption of acceleration acceleration motion your assumption of motion direction is opposite lah, is terbalik, is opposite. So for example, you say that, oh, this object has motion going to the right, but your answer for acceleration is a negative magnitude. It simply means that your assumption terbalik. That is all. You don't have to rewrite everything. You don't have to draw a new free body diagram. Just say that the actual motion is to the left instead of your assumption. You won't be penalized if your assumption is incorrect, because it is part of solving the equation lah. So part of solving the forces. You can't, I mean, if you don't know, then you don't know lah kan, kena lah assume kan. So sometimes it's correct, sometimes it's not correct, and you won't be penalized for it. But the magnitude akan sama walaupun ke kanan ataupun ke kiri, magnitude akan sama if you don't have friction. Okay, again, I'm going to repeat myself here. So your acceleration, when it's negative, it means that your assumed motion is terbalik. It is in the opposite direction sepatutnya. So this is the actual motion. But the magnitude should still be the same walaupun arah terbalik. Magnitude is still the same. This is exclusive to if your free body diagram does not have friction. Maksudnya the incline is smooth, or basically there's no friction lah. The street is smooth, macam tu lah. Situasi yang tak ada friction. Okay, so that is your recap. So let's go back to our final example for this. We've done this one. Have we done this one? We want to go over a smooth incline. Kita nak cari yang smooth incline. Let's see, ada tak yang smooth incline? Okay, this one. This is from your web assignment. So let's do this one. Two packing crates of mass M1 equals to 10 kilogram and M2 equals to 3.1 are connected by a light string. Okay, why do I need to remember when I have a string? What force is there? Okay, tension or T. Okay, correct. So you have tension or T. So the T, let me make this bigger. Why is it so small? Okay, so your T goes here. Oops. Okay, this is your T and this is your T. Are the T equal? Are the T equal or not? Yes. Why should it be equal? What's the keyword here? Oh, frictionless pulley. Frictionless pulley, This is the keyword. When you see a frictionless pulley or a smooth pulley, it means that your tension on both sides will be the same. Kena ingat this keyword. Okay, so tension is going to be the same on both sides. And then we have our gravity, macam biasalah. Mg over here, and then mg over here. Okay, what else do I have for M2? Same rope connected. Okay, betul. What else do I have? mg sine theta, mg sine theta, r. Okay, so we have r, mg sine theta will, this is your theta over here. This will be mg sine theta, going downwards here. Oops. Stop there. Hello, wake up. Lama pula dia recover ni. PowerPoint ni kenapa? Hello, bangun. Hai, saya tak ada tulis dia macam ni. Oh, my last week is, ni week 7. Week 8 is next week. Week 9 lagi 2 minggu. And then week 10 saya dah tak ada dah. Nangis. Tapi nanti bila korang dah masuk asasi, nanti kita jumpa lah, okay? You don't have to be in my class to see me. You can always see me. Okay. Okay. Where were we? Okay, so we have mg sine theta, right? So this is mg sine theta and this is mg cosine theta. Okay, my question is, does M1 have R? No. Okay, correct. M1 does not have R because it's not on a surface. Okay, so there's no surface here. It's suspended in air, so there is no reaction force. Kalau korang suspended pun tak ada reaction force. Kalau timbang atas, if you are suspended, you don't have reaction force. If you put a weighing scale down on your feet, kiranya ni shaky lah. And then ke bawah ni Amy ni shaky tengah suspended. Shaky is not ni it's not doing anything weird here. She's just suspended. Dia atas bakul lah. Dia atas bakul supaya kita semua bertenang. Okay, this is not a trigger. Please do not be triggered. Okay, so sabarlah di dalam bakul. Okay, so Amy dia letak weighing scale kat sini. Tapi bakul ni suspended dengan shaky. Bakul ni suspended. So when it is suspended in air and you put a weighing scale on something that is suspended, what does the weighing scale detect? Is it able to measure shaky? No, right? Kalau kita fikir logik pun lah kan. Kalau ada benda tergantung, so I'm like putting it, I'm like, oh sorry, what is this? Buat kantor. So I have my pen here and I want to know what is the mass, contoh lah. So I am pegang, I'm suspending it and I put a weighing scale, but at the same time it is suspended. I won't be able to measure the weight, right? Kalau saya nak measure weight, saya kena letak atas the weighing scale. But if it's suspended, I'm not actually putting the weight of the pen on the weighing scale. So there is no reaction force. Therefore, the weight does not measure anything. So like I told you before, the weighing scale measures your reaction force. If there is no reaction force or you are suspended in air, then you will become very, very light or no weight at all. So kalau nak kurus, boleh guna cara tu, suspend yourself. Ya Allah. Okay, so let's continue. So that was just like a trivia. Okay, so we have mg sine theta, mg cosine theta, tension, reaction. So this guy, the 3.1 kilogram crate or the mass 2 is on a smooth incline. Okay, smooth incline, which means that there is no friction. No friction. So here our free body diagram does not have friction. So dah betul dah lah ni. Okay, so now it's asking for the acceleration of the 3.1 kilogram crate. So it's saying that up the incline. Dia dah bagi motion siap-siap. So that's great. So let's say I want to, this was not given to me. Let's say it was not given to me. So I say, oh, motion dia, I want to guess it's this way. Let's try it. The motion is this way. Sekejap, before that, let me see kalau kita ada jawapan ke tak. Saya lupa saya ada jawapan ke tak. Sekejap nanti kita tak boleh nak check kita punya terbalik tu sama ke tak. Give me a minute. I want to prove to you guys that the magnitude is still going to be the same walaupun assumption kita salah. Okay, so let's do that. Chapter 3. View. Chapter 3, soalan nombor 11. Soalan nombor 11. Okay, let's go back here. New slide. Okay, sebab saya punya web assign nombor dia lain, let's use this number. So M1 is 10, M2 is 5.5, and theta is 33. 10, 5.5, 33. 10, 5.5, 33. M1 is 10, 5.5, and theta is 33. Nanti kita tengok sama ke tak jawapan kita. Kita nak buat assumption yang salah. So let me make this bigger. Okay. So free body diagram should be the same, only the values yang lain. Macam korang punya web assign juga. Saya punya web assign pun jawapan lain juga daripada korang. So I won't know what you guys punya value are. Sebab tu saya tak boleh nak bagi jawapan pun. Kena buat juga. So draw. Okay, so we start with our condition. We know that this guy is supposed to move. It has acceleration, right? So we know that the condition will be MA somewhere. So for mass number one, what is equal to MA? Is it net in the FX or is it net in the FY? For mass number one. Mass number one yang ni, tergantung ni. Is it FX or FY equals to MA? So Safa, Afriza, and Soh is saying FX. FX. Wafa is saying FY. M1 is this guy. Okay, let's look at our axis. This is the X axis. This is the Y axis. Yeah, it should be Y, right? Okay, and then for this guy, this is the X and this is the Y. Sorry yang kecil. So sebenarnya kat sini, our FX is parallel to our motion. Our FX for mass number 2 is parallel to the motion. Apa ni? This is FX. But untuk mass number 1, the motion is in the FY. So boleh berbeza axis? Boleh. So in mass 2 yang atas crate ni, atas incline, it is moving this way. Kan? So that is in the x-axis. But when this guy is moving left or right, this guy will move up or down. So yang bergerak dalam mass number 1 is in the y-axis. So untuk mass number 1, our y-axis is equal to MA. Tapi untuk kita punya mass number 2, it is going to be FX. This is something that you need to take note of. So mass number 1, net in the FY is equal to MA. Net in the FX is not moving left or right. So this is going to be equal to 0. And for mass number 2, it's going to move left or right on the incline. Therefore, it would have Fy equals to 0 and net in the Fx equals to MA. So here they said that the motion is up the incline. So kita akan cakap, kita nak buat assumption yang salah kat sini. So we are saying that it's going down the incline. This is our motion A. Okay, so let's do it. So net in the Fx equals to 0 for mass number 1. Tak ada, there's no forces in the x-axis. Therefore, we don't have to solve it, just leave it as it is. Net in the Fy is equal to MA. We have tension going up, so I'm going to say that going up is positive, going down is negative. So we have net in the Fy equals to MA equals to T minus mg. Okay, so mass is, this is 5. And this theta is 33 degrees. Saya ada soalan ke? Sekejap, saya tengok. Boleh, boleh Wafa. Boleh Wafa. Okay, semua orang siapa yang nak pergi toilet, pergi je. You don't have to ask for permission. Tapi bila saya panggil nama nanti, kalau korang hilang, bagi tahu je lah pergi toilet. Okay, so net in the Fy equals to MA equals to T minus mg. So this is what you have. So M, the mass is still the mass, the same mass. There's no other mass here. We are talking about mass 1. So this guy should also be mass 1. Jangan pandai-pandai letak mass 2 pula. So this is M1 and M1 as well. So mass 1 is 10. I don't know what my A is. I don't know what my T is. This is 10 and this is 9.81. Okay, so this is what we know so far. Next, for mass number 2, net in the Fx is, net in the Fy is equal to 0. And this is equal to R minus mg cosine theta. Because I have R going up here and mg cosine theta is down here. Lupa buat arrow. Okay, so now I know that my R is supposed to be hilang. Okay, so R, kita perlu ke solve for R? Let's just do it. So R is equal to mg cosine theta, or in this case, it's mass 2. Mass 2 is 5 times 9.81 times cosine 33. And then for net in the Fx, okay, net in the Fx is equal to MA. This is M2A. Is equal to, what do we have in our x-axis? We have mg. If this guy is going up, is positive, right? Tension going up is positive. This guy kena sama. Kalau bergerak macam ni positif, bergerak macam ni kena positif. Okay. So your positive sign is to the right of mass 2. Positive sign. So that would be mg sine theta minus t. Okay, so rearranging this equation, this is M2G. So rearranging this equation, I want to solve for T because I want to get rid of it. So this is going to be M, positive, negative, go here, positive. So I bring this guy over here. M2G sine theta minus M2A. Okay, and M2 is 5. 9.81 sine 33 minus 5a equal to t. So I want to get rid of t because we have two unknowns here. I can't solve for two unknowns because this is not mathematical. Kita nak pakai calculator simple je. So I solve for t in here as well. So this would be apa tadi? 10a plus 10 times 9.81. Kenapa saya buat equals to t? Because I have two unknowns here. I have acceleration as my unknown and my tension as my unknown. So I don't know the values for these two things. But I don't want to solve for tension. My aim here is to solve for acceleration first. At least this is what the question is asking. So I need to get rid of tension first and solve for A. So T and T here are equal. We know this because they are connected by a smooth pulley. So kita boleh equate them together. So 10A plus 10G equals to 5G sine 33 minus 5A. 5G sine 33 minus 5A. So we only have sine theta here. Kat sini tak ada sebab dia tak ada angle. Okay, betul. So next, I rearrange this. I bring this guy to the other side. So we have 15a, and this is 5g sine 33 minus 10g. Okay, so now I can solve it. So 5 times 9.81 times sine 33 minus 10 times 9.81 divided by 15. Tolong double check my kerja. I get minus 4.76. Dapat sama tak? So korang kira jap. So I know I can simplify this equation tapi saya tengah malas. So ada orang dah dapat jawapan ke? Sama. Okay, thank you Afika and Farah. So we get acceleration as minus 4.76. Now I get a negative magnitude, which means that my assumption for the motion is wrong. Sebab jawapan memang cakap up the incline, ni dia bagi. Tapi saya cakap, okay, saya nak assume dia terbalik. So I say that the motion is down the incline instead of up the incline. So it's down the incline, and the answer that I got is a negative, which means that, yeah, indeed, my assumption is wrong. Maksudnya, the motion is up the incline. Therefore, I can write this as the acceleration is 4.76 up the incline. Okay, so I use this number, but I say it's up the incline instead of going down. Okay, you can describe it like this and it will be correct. You don't have to change anything. Now let's see if our value is actually the same. 4.43. Dapat berapa? 4.76. Jauh juga ni. Sekejap, let's see. 4. Oh, this is 5.5. Dang. Kejap. So mass 2 is 5.5. Saya tersilap. Saya letak 5 je. So let's see if this is actually correct. So this is going to be 5.5. 5.5, So 5.5 times 9.81 times sine 33 minus 10 times 9.81 divided by 15. 4.58. Tak sama juga. 5.58. Ada lagi yang tak tersilap. This is 5.5 minus, oh, 5A ni. Okay. Saya tersilap lagi. Kat sini saya tersilap kat sini. So this will be 5.5 and 5.5A. Kita kena buat betul-betul sebab saya nak buktikan magnitude dia sama. Kalau tak saya malas ni. 5.5A. Okay, so equating this guy, this would be 5.5, 5.5. Okay, so this will become 10A plus 15. So I have 15.5 here. 10 dengan 5.5 over here, 15.5. 5.5g sine theta minus 10g. So this does not change. Okay, so let's see what the actual answer is. Hopefully this time it's correct. 5.5 times 9.81 times sine 33 minus 10 times 9.81 divided by 15.5. I get 4.43. Is that the right answer? 4.43. I get a negative sign meter per second squared. So the acceleration is 4.43 up the incline. Let's see the answer. So it's 4.43. Sama jawapan dia. So here, even though my assumption is wrong, my assumption I said it was going down the incline, my assumption is wrong, but it doesn't mean that my answer is going to be wrong. So this is your proof here. So jangan panik lepas ni. Okay, so that is it. This is the last example. Let's continue with chapter 4. Do we have any questions about this problem? Alah, kena buat tension ke? Okay lah, kita buat kejap. Tension is equal to, ambil yang senang. This guy, 10A plus 10G. This is 10, 4.43 plus 10, 9.81. Tu tekanlah calculator sendiri. Okay, kalau nak solve for tension kan, you can pick either one. It will give you the same answer. Tension kalau pakai equation ni akan sama, pakai equation ni pun akan sama. assuming that your acceleration punya value betul lah. Kalau acceleration punya value salah, salah lah. Okay. So that is how you do it. Okay. Any questions? Everyone is okay? Everyone understands what's going on? Kenapa saya buat assumption salah? And what happened after that? Ada tak yang blur? Okay, everyone's okay? No questions? Going once? Twice? No? Okay. Let's start with chapter 4. Oh, ada chat kat sini jap. Okay, so everyone is okay. So let me save this. Lamanya. Okay, let me. Excuse me. Lamanya. This is your break, by the way. Kita kelas sejam je, Thailand nak kasih break. Tak cukup masa. TikTok. Wait, apa salah dengan PowerPoint hari ni? My God. Or is it my laptop? Does anyone want to share any random facts today while we wait for PowerPoint? Oh, okay, save. Oh my God. Okay, finally. Tutup. Doktor dah start engineering ke? Tak. Semester engineering start October, not yet. So asasi dengan degree punya semester tak sama. Fun fact, Amy tak mandi lagi. Nanti saya beli iPad. Wah, banyaknya duit saya. Sekejap nak go for PowerPoint chapter 4. Okay, am I sharing? Not yet. So saya dekat Jabatan Sistem Komputer dan Komunikasi Kejuruteraan, itulah lebih kurang. So not EE, walaupun saya degree saya EE. EE means Electrical Engineering. Okay. Okay, so we are doing chapter 4 now. Kita sempat sikit je, sekejap je, tak apa. Let's just go for an intro. Doktor bila boleh dapat markah? Bila? Saya kena tunggu bos saya approve markah semua orang dulu. Saya tak tahu lagi, nanti saya bagi tahu. Saya rasa next week kot. Next week boleh kot, insyaAllah. Nanti boleh ke minum kopi sama-sama? Boleh lah, tapi make sure you are double dose vaccinated baru jumpa saya. Saya takut juga. Pakai double dose lepas tu jangan demam-demam. Okay, kalau nak jumpa saya, boleh jumpa saya anytime. Tapi Haikal kena belanja lah. Okay, betul. Boleh jumpa, kita jumpa dekat dekat UPM ada cafe tau, nama dia He and She. Saya selalu lepak situ before class sebab saya suka belajar. I prepare my lectures dekat cafe tu lah. Tapi kalau Haikal datang kacau, saya tak dapat belajar lah. So macam itulah cerita dia. Mahal ke tak? Kopi dia macam RM8 ke RM9 macam tu. Dia bukan Starbucks. Bukan Starbucks. Tapi coffee dia sedap. So if you like coffee, I think you will like that place lah. It's really good. The coffee is really good. And then dia ada salted egg croissant, ada cakes, ada spaghetti. Tapi spaghetti dia tak berapa sedap. Dia punya nasi Arab okey-okey lah. Tapi yang paling saya suka is the salted egg croissant dengan coffee, cappuccino and latte dia. Itu sedap. Nanti korang try bila dah masuk hostel nanti boleh pergi situ. Dekat je, dia di sebelah main library. Nanti korang ada orientation semua tu, nanti korang tahulah kat mana. Okay, so please look forward to that. It's a quite nice experience lah, I would say. Best juga duduk hostel ni. Okay. And you get to hang out with your friends. So that's the most important part. So we are talking about chapter 4. Chapter 4 is about work and energy. So ada kaitan tak dengan chapter 3? Of course ada. So kita dah belajar free body diagram and forces in chapter 3. For this chapter, we will apply the free body diagrams and also the forces. So after completing this chapter, you must be able to define and calculate work by a force, relate between work, energy and power, understanding the work energy theorem, and then state conservation of energy and solve related problems. So conservation of energy ni, you call it keabadian tenaga in Malay, if you are familiar with that term. Okay, keabadian tenaga. Okay, so don't know why this guy is here. Tak tahu apa relation dia. Okay, so this is work done by a force. Okay, so when force is applied on an object, we know that when we have force, we have acceleration, right? This is equal to the change in velocity or acceleration. And when we have motion ataupun acceleration, we will have displacement. So whenever you have force and you have displacement of that object, there is actually work done by the force. Work done on the object by the force. So when you have force and displacement, you have a change in displacement of the object, you will have work. Okay, kena ada dua komponen ni. Kalau you only have one of each, if you have only one of it, then it won't become work done. Okay, so kena ada, when you have force, there will be a change in velocity ataupun you will have acceleration lah. Okay, this is the condition. And displacement ni, displacement je lah, displacement biasa. Okay, so now, let's take a look at this diagram. So work done, I'm going to introduce to you the equation. So work done, we label it as capital W. Macam force kita label as capital F. So work done is labeled as capital W and it is equal to F vector dot displacement vector. F vector dot product with displacement vector. So if you guys still remember, dot product, when you expand a dot product, it will become F magnitude delta X magnitude cosine theta. And what does theta mean? Theta is the angle between the two forces. So if this is F and this is your delta X, this is the angle between them. Is this angle between them. So it can be anywhere. It can be like this, F, this is F, this is delta X, boleh. This is the angle between them. So I don't really care which axis the force and displacement is. I only care about the angle between them. This is what we learned about dot product last time. But in this case, our motion is most likely to be in the x-axis lah. Sebab motion of object kan. So we are going to say that displacement is typically in the x-axis. Therefore, the angle between force and displacement is going to be with respect to the x-axis. Tapi yang sebenarnya, when we talk about dot product, we are just concerned about the angle between the two vectors. So jangan confuse kat sini. Kalau tengok dia refer with respect to x-axis, it's because it wants the angle between the vectors, not necessarily with respect to the x-axis. So if your displacement was like this, delta x, and your force was like this is with respect to, I don't know what this is, what axis this is, but this is the theta because this is the angle between the two vectors. Okay, so this is the definition of dot product. Now, if you have a dot product, it will give you a scalar quantity, not a vector quantity. So you will have a scalar quantity. What does it mean when you have a scalar quantity? It means that it doesn't have, it's not a vector lah. It's not a vector, or it does not have direction. Dia ada direction, tapi direction dia ke kanan atau ke kiri je. Positif, negatif, macam tu. Tapi it's not a, macam mana nak cerita? It's not a vector. Ke kiri, ke positif dengan negatif ni kita akan tengok apa dia maksud positif dengan negatif tu. It doesn't mean direction It just means, it means something else lah. I will tell you later. Okay, so it's not a vector. I can tell you that much. It's not a vector, it's a scalar quantity. You won't have angles associated with your answer. I'm going to repeat myself, you won't have angles associated with your answer. I only want to know what is the magnitude for work done. Okay. All right. So what else? Okay, let's look at this example lagi. So in this case, this box is being pulled by this lady to the right. So we can say that the displacement of this box is to the right. So this is your delta x. So this lady is pulling this box by a vector, by a force. The force is called F. And if I wanted to know what is the angle between F and delta x, it is theta. So I resolve my F to become F cosine theta because I want to know what is the component that is parallel. I want to know what is the component that is parallel to my delta x, and that component is F cosine theta. So F cosine theta and delta x will give me work done. F cosine theta and delta x will give me work done. Sama tak dengan dot product? Sama. It's exactly the same thing. So this is what it means. It only wants the parallel component. Nampak ni? Parallel sign. So this is the force that is parallel to the displacement. We only want the force that is parallel to the displacement. Okay, let's look at this piano pula. So look, draw my free body diagram. I have mg going down. I have a pushing force by this guy. So it's going this way, F. And the displacement of this piano, assuming that orang ni boleh tolak lah, dia kuat kan. So the displacement is also this way. This is delta x. So the pushing force, I'm going to label this as Fp. The pushing force is parallel to delta x. Therefore, the work done on this piano by pushing force is Fp delta x cosine theta. But in this case, the theta between Fp and delta x is 0. Theta is equal to 0 sebab sama kan, dia sama direction, so angle dia kosong lah. So Fp delta x cosine 0 is equal to 1, so you just have Fp delta x. So this is the work done by the pushing force on the piano. What about our gravitational force? So we have several forces here. We have pushing force, we have mg, assuming this is a smooth incline, so we don't have friction. So gravitational force, direction dia macam ni. Direction dia macam tu. Kita padam dulu The direction of mg is down here, and I have my displacement is this way. So I want to know what is the parallel component of mg to delta x. So I resolve this guy. This is from chapter 3. I try to resolve it. So this is going to be mg sine theta. Assuming this is theta over here, this is going to be mg cosine theta. Okay, so tadi kan kita tengok work done by the pushing force was Fp delta x cosine theta, this guy was 1. So you had FP delta X sahaja. FP was in the same direction as delta X. So you got, let's say FP is 10, delta X is 10, you get a positive answer. Okay, so this is what we had just now. Now we are talking about mg now, or weight. I'm not going to label it weight, nanti confused dengan work done. So now we have weight. I want to know what is the component parallel to delta x. It is mg sine theta. So I write my equation. Work done is equal to mg sine theta. Saya dah terus pakai parallel component kan. Kita cuba tempat pula pada bawah ni. So work done is my out of time. Sekejap sikit lagi. Mg sine theta delta x. And what is the angle between mg sine theta and delta x? It is in the same, it is 180. It is 180. Delta x, angle between delta x and mg sine theta, angle dia adalah 180. 180 So cosine of 180 will give me -1. So my answer is minus mg sine theta delta x. So work done is negative by the gravitational force. Work done is negative by the gravitational force on the object. Work done is positive. Work done by the pushing force is positive on the object. So kita tengok kat sini, forces that is in the same direction. Forces that is in the same direction as displacement will have a positive work done, and for forces that is in the opposite direction as displacement will have negative work done. And again, you only take into account the parallel force to the displacement. Okay, so that's it for today. We will continue next class. Any questions? Okay, Jannah, bye. Maknanya semua direction ada different work done. Maknanya semua force ke maksud awak, Amy? Maknanya semua force ada work done, betul. Kalau ada displacement, kalau dia parallel to the displacement. Siapa lagi? Matters power ke tu? Ada soalan tak? Tak ada No questions. So Amy is asking, does all the forces have different work done? Yes, it will have different work done, but there is a shortcut to this. So nanti kita akan belajar shortcut tu. Tapi buat masa ni saya cerita satu-satu dulu. Okay. Student boleh lepak situ ke? Dekat kafe tu ke? Boleh. It's open. Okay. Yay, saya introvert lah doktor. Amy introvert. Betul ke ni? Okay, Farhan tanya, kita hanya cari force yang parallel dengan displacement saja kan? Ya, betul. And that parallel force can either be cosine 0 or cosine 180. If it's cosine 0, then it's a positive. If it's a cosine 180, it's a negative work. Doktor, kita boleh outing ke? Tak tahu, yang tu saya tak tahu. Yang tu ikut kebenaran college. Kalau korang kena quarantine, then get ready lah. Saya tak tahu. Kena tunggu arahan. Yang tu ikut pengetua. Okay, tak ada So 5 minutes to go. No questions? Okay. Okay, so dah excited pasal cafe. Dia dah tak ingat dah chapter 4. Okay, bye guys. Have a great rest of the day. Have a good weekend. Hopefully by next week kita boleh tahu markah. Okay, bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Welcome, bye-bye.
Thank you, Doctor.
Welcome, bye-bye. Welcome, Wafa, Munira. Okay.